Hey guys, it's IDW, and today I'm going to be going over 2's complement in binary, which is a new way of doing subtraction that's different from 1's complement, which we went over in the previous video. But yeah, the main advantage of 2's complement over 1's complement is that you can have negative numbers instead of just random digits, and knowing that it's negative but not being able to translate it. Anyways, so the other thing about 2's complement that's an advantage over 1's complement is with 2's complement, you don't have -0. With 1's complement, you can't technically have it, and therefore 2's complement is a counting system that is technically always true. So, yeah. So, they're basically the same thing, though, and they just have a few slight differences, which we're going to be going over right now. And, yeah, make sure you watch the previous video, though, because we went over most of the logic that we're going to prove, that basically goes into how a subtractor works in that one. And also, the other important thing that you should probably know coming into this is that, all that 2's complement is it's really just another way of doing 1's complement that just is slightly easier to use for negative numbers. But yeah, without any further ado, let's just dive into what exactly are negative numbers in 2's complement. So yeah, so we cannot change the inverting of the inputs that we have at the very start, except for which input we need to invert, which may actually come up. Hint, hint, it will. Anyways, let's look at another problem that we actually had when we were actually trying to build our first subtractor. If we had to invert one of the inputs, and we had to specifically invert one of them, not both of them, otherwise nothing would change except for the carry, and that would get messed up. Anyways, but because we inverted that input, we were left with an XOR NOR for a first XOR, and an XOR for a second XOR. And the problem this resulted in was our output was inverted, which we didn't want to happen. So what we ended up doing was we just ended up inverting the output. But since we can invert the output of an XNOR by inverting either of the inputs, there is another option that we actually have. So if we want to invert the carry, then we need to basically make it so that we are always carrying into a bit, unless we actually want to carry. I know it's difficult for you to wrap your mind around, but yeah, that's basically what it would mean to invert the carry. It's a bit complicated to prove, but once we get it into practice, it's going to be actually pretty easy. So, anyways, let's assume that, for the moment, that we have a signal that comes into the current bit that we have. Let's try to find a certain way that we can make it so that it will only turn off when we actually want it to carry over to the next bit, which coincidentally is the time when basically sorry, I'm rambling right now, but basically that's the only time that we want it to not carry over is if we have that scenario that we discussed in the previous episode where we have 0 minus 1. So yeah. Okay, so since right now we just have to wait a minute, now that I think of it, 3, 2, 1. So since we're assuming that we have a carry coming into the bit in question, in order to make sure that we are quote-unquote uncarrying in the right scenario, is if the truth table of the inputs makes it so that the output into the next bit is false when we need it to be and true when we need it to be. So yeah, and we may actually have to change the way that we've inverted our inputs. Hint, hint, we will. Anyways, so if you think about it, if we have our inputs at 0 minus 0 and 1 minus 1, that's not actually going to affect the carry line, is it? So as a result, yes, it doesn't. And that's because we have an XNOR, right? So that means that if we have, well, our first XOR has been turned into an XNOR. So if we have a signal coming into that particular bit, then we know for a fact that we'll carry it over to the next bit. So that takes care of those two already. Boom. Anyways, so now the next thing that we're going to have to take care of is the only two remaining scenarios that we can get. We can get 1 minus 0 and 0 minus 1 in each bit. So the only time that we actually want to carry over to the next bit or give a true value to the next bit is if we have 0 minus 1. Well, give a false value to the next bit since we're inverting the carry. So that means that we're going to have the output of our first AND gate in our first XOR on when when we have 1 minus 0. And otherwise, when we have 0 minus 1, there just won't be any carry that moves on to the next bit. Anyways, so that means that the way that we generate the carry is we invert the negative one so that we have both of our inputs are on when how could I describe this? Both of the inputs into the AND gate are on when we just have that one input on, because that's because we just want to have our positive on and our negative off. And since it's inverting the input into the adder, it'll be our positive on and our negative on as well. So that will give a true value that it will carry over to the next bit. So, yeah. So basically, we're going to have to invert the other input. So the negative input is now the one that gets inverted. The next thing that we have to address is we have to make sure that the carry's natural state is on. And the easiest way to do that is just to carry in and then assume that each bit gets a carry in. But what if it doesn't get a carry in? Well, that would mean that we were carrying over from a previous bit, correct? Well, the only time that you actually want to restart the carry from there is if you have, in that particular bit, 1 minus 0. In any other case, it wouldn't actually matter. 1 minus 1 wouldn't matter. 0 minus 0 wouldn't matter. But 1 minus 1, it would actually matter, because then your result wouldn't be negative, and you wouldn't just keep passing it on. So since that's the only case in which the AND gate turns on, it will work just perfectly. And I know this sounds incredible, but if we just carry in right here, we have a full 2's complement subtractor. So let's just take a redstone torch, plug it in here, and we have ourselves a 2's complement subtractor, which ripples along. And also, since the carry isn't inverted, our carry out is technically inverted, and therefore, if it's positive, if the output is positive, then it will be on. If it's negative, it will be off. But since we can just put our negative input into this input right here, let's actually try to do some stuff with this. So let's do 3 minus 5. And our result should be 2. And as you can see, our result is in fact 2. But what about the negatives, you may ask? You told me that in this episode we were going to be incorporating a way in which we could do negatives, and with 2's complement you can't actually do negative numbers. However, how to translate them is going to be a deal for the next episode. So yeah, hope you guys enjoyed, hope you could understand. Sorry, this is not the easiest topic at all. I'm sorry that... Anyways, hope you enjoyed, and see you guys next time.